talking about relating graphs to events. And this is something you definitely should have done before as well. I want to make sure we're sort of filling in some pieces and we really have a solid, firm ground on this, because graphing and talking about what graphs mean are never, it's just not going to go away. It is one of the most important things that we do in math. Okay, so first of all, when we are talking about a graph, typically we are looking at only quadrant 1 in the coordinate plane. So right, we really have more of a coordinate plane happening, but we tend to just be in quadrant 1, where we have our independent variable on the x-axis and our dependent variable on the y. Hopefully we're like, yeah, definitely like heard those things before. How do we decide what our independent variable is? Gavin?
The x.
I mean, it is the x, but how do we know what the x is? Tavian?
Because the x is horizontal and then a graph.
I mean, that is what it is in a graph, but like if we're looking at a problem that's talking about how much money we make based on the number of people that come to the movie theater, how do we decide which one is independent? Lily?
It's the one that's the changing.
Yeah, so that's science, right? Because when you're doing an experiment, it's what you're taking. You're right. Yeah, you're right. That's definitely what they tell you in science. We need a little bit more broad, completely works across the board. Okay, what do you say?
Isn't it the one that goes by itself? Or like...
Yeah, so it's the one that kind of stands alone. The way that I sort of like to phrase it, it's the one that has to happen first. Okay, so do people come to the movie theater and then we make money? Or do we make money and that brings people to the movie theater? Well, people come and then we make money, right? So our people would be the independent because that then affects this one, right? This relies on this. People can come and go no matter what, but we're not going to make money unless people come. Now, if we can't find what the independent variables, so we're looking at a problem like, I don't even see two things, guess time. Time is usually our hidden label for our independent variable. Okay. Then in a graph, there are three things that could happen, and hopefully we realize that this is true as well. The graph can go up. The graph can go down. Or the graph can be flat. I know that's not super exciting information, yet no matter how many times I tell my students this, they change their minds later in class. What do we say if it's going uphill?
Pocket.
I mean, that's what the line is doing, but like increasing, right? And it's increasing per whatever our y label is. So if it's money, we have an increasing amount of money. If it's going downhill, what do we say? Decreasing. So in this case, decreasing amount of money, right? Whatever our y label is. What does the flat section mean?
Stop.
Stanza. Constant.
Constant is the word that we use here. How do we feel about those three labels? Do we agree with them? Like, we need to agree. Thumbs up, we say we agree. Okay, because our minds can't change in just a few minutes, and so far, let's see, this is round 6 of teaching it. So far, everyone's mind has changed, but we'll see if you guys are the last one and can get it. So if you're trying to manage how much space in your notes, we're going to do 4 graphs total. Okay, so here's our next graph. Okay. So we're going to do my distance from the door. So I'm going to start by standing right here. Where does that mean my graph is starting?
0.
At 0, right? I'm 0 feet away, 0 time has passed, so this is technically 0, 0, right? But I'm starting here. Yep, the origin. Okay, and I start walking. What's happening in my graph? It's increasing. Okay, so I'm walking, it's increasing, it's increasing, it's increasing, it's increasing. Okay, now I'm going to stand here for a little bit. And now what's happening? It's constant. Pretend that's straight. Right? Standing here, I'm standing here, I'm standing here, I'm standing here. And now I have this.
Like almost straight down.
Oh, we don't want to be almost straight down. It's not quite that much. But why are we saying something about faster down?
It took you less time to get to the door.
Right? It's less time with the same amount of distance. Okay, so less time with the same amount of distance. What does that make happen with this line? What word could we maybe use with that? It's steeper. Now, the math term that we associate with that is slope. Hopefully we've heard that word. You haven't talked about it yet this trimester. You're going to do more with it tomorrow in e-learning. Okay, slope is telling us how steep that line is. Okay, the steepness of the line, I'm not honestly 100% sure that that's a word, but it is now. I keep using it. So the steepness of the line is going to tell us the rate. In this case, because we're talking about speed, the steeper the line, the faster we're going. Okay, the more shallow the line, the slower we're going. So far, so good? Okay, so now I'm going to do this. I'm starting at the same place, still over here at the door, but now I'm going to do this. How are we going to graph that? Well, what were you kind of doing there, Taylor?
Well, like, it goes up slower than like.
Yeah, so this is the motion you're doing with your hand. What is this motion?
Curve.
It's curved. Okay, so we end up having a curved line. Now, I'm not saying that this curved line matches up perfectly with what it would be in comparison to the other one. I'm just saying, okay, a curved line means it's a non-constant rate. Okay, so just by looking at a graph, we can determine several things, right? If it's a straight line, I can tell, okay, that rate is happening consistently. I'm not changing, in this case, my speed. Okay, it could be the number of cookies I'm shoving in my mouth. I don't know, right? I'm eating them at the same rate, whatever. Okay, whereas a curved line is telling me that that's changing over time, right? Slow, 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 faster, 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 faster. Right? And I also can tell then by how steep it is whether I'm going faster or whether I'm going slower. Right? We can determine all things. Do we agree?
Yeah.
Okay, so why do we graph things? What is the point of this? Davian, what do you think?
So we can show like the rate of the distance throughout a period of time.
Yeah, but I could show that other ways, right? Couldn't I show that in a table as ordered pairs? I could write down some words and talk about it. I could write a function rule. Alex, what do you say?
Visual representation.
Why might that be helpful?
Because it lets you imagine it in your head instead of words, and it's
Okay, so I think all of us have probably been guilty at some point of going, ew, math, words, math and English do not go together, right? That this allows us to sort of see that information in one little snippet. Okay? Now, we have to be careful because there's only a certain amount of things that we can get from the data, right? We're representing data, we're representing information in a graph. It's an easy visual cue to sort of see what's happening with all those different things in one quick look. Okay, we just have to make sure that we are taking it for exactly what it is. Okay, so we're going to keep going here. I'm starting over here again. I'll be talking about time and my total distance. What's happening? It's increasing. Should it be steep or should it be shallow? Should it be straight or should it be curved? Straight. Right, I'm standing here, standing here, standing here. So now what's happening? I'm constant. And now what's happening?
Speeding up.
Fast.
Decrease.
Increasing.
Santes is increasing.
You can't decrease on this graph.
Why?
Because it's total distance and you keep on moving, it doesn't matter which
It's
direction.
total distance. I have walked 1, 2, 3, 4, 5, 6, 7, 7, 7, 7, 7, 7, 8, 9, 10, 11, 12, 13, 14. Now I'm doing it faster, so my line is going to be steeper, but what way does it need to go? Up. Yes, Avian?
That doesn't make sense if you're doing the total distance by time. Like, if you're doing the total distance from the door to the desk.
No, no, no. I'm not doing my total distance from the door. I'm doing my total distance. How far have I gone? I have gone 1 step, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps, 7 steps. Doesn't matter what direction I go. My next step is step 8, 9, 10, 11. Because in total, we can't change directions. Now, you have to be a little bit careful with this one. Because sometimes there can be other things affecting what we do. Like if it's talking about the total number of miles I ran in a day, which is always 0. Let's be clear, I don't run. But a new day would reset that information. Now, it doesn't always just have to be going up. For example, what if I talk about the total number of cookies in a cookie jar, and I eat 1 cookie per day? Which, let's also be real, who really just eats 1 cookie, but whatever. I'm eating 1 cookie per day. What is that graph doing?
Decreasing.
It's decreasing. The only way that that can go back up is if something else is at play, like I make more cookies and I put them into the cookie jar and then I reset it. Does that make sense? Are we okay on that? Okay, last graph. This graph is going to represent my bike ride. And I'm talking about my distance from my home. Okay, so I'm going on a bike ride and I'm going to graph my distance from home. Okay, and here's how I'm going to represent my bike ride. So what's happening first on my bike ride? Okay, so my speed is quicker, and what am I doing? I have an increasing distance from home. Reasonable, right? Now what happens?
You're going at a slow speed. You're going on the thing.
You stay in the same
stop.
place.
No,
Stopping.
if a graph goes like this, and you're riding your bike, if you're going like,
This isn't talking about my speed. This is talking about my distance from home.
yeah,
Haley?
You're not leaving your distance, like your distance from your house isn't changing.
Okay. So remember how I told you those 3 words earlier we needed to stick to? And then right here we all just left those 3 words? Because how many of us are like, yeah, we stopped. We stopped. Now, our brain sort of fills in pieces. Remember how I said that? All this technically tells us is that we are a constant distance from home. So let's say this stool is my home. Okay, I rode my bike away from home. And now I'm going to do this. Is my distance from home changing? But did I stop? No. Does this graph tell me that I stopped? No. Now, could we guess that we stopped? Sure, but would we necessarily be correct? Not necessarily. Does it seem more reasonable that we stopped? Sure. What would we need to know to have information to decide whether or not we stopped? Santi?
Total distance traffic.
No, that won't necessarily help us. Elijah, what do you say?
Total distance from home.
No, you guys are thinking too graph. You're too stuck on a graph. Lily?
Maybe just like total distance, not from home, just total distance.
What if I just told you the story? What if we just read the words about what happened? Would that tell us? So if instead of looking at just the quick graph of info, I now needed to read something to get some more specific details, would that give us the information? Yes. Now, there are some other things that we can fill in if we are given permission to sort of guess, but we don't know for sure. What if I told you, you know what? This is my bike ride to my friend's house. And between my house and my friend's house, there's a hill. So now I'm giving you some more information. Okay, which way did we most likely ride our bike uphill? Where? I heard something, but I didn't. Where are we most likely riding our bike uphill?
Whoa.
To our friend's house or away from our friend's house?
2.
no way.
No, yeah.
Wait, no, it's to your friend's house because you said you're riding it uphill. And there's.
I just said there is a hill. I'm not saying which way you're riding it.
Well, if there's a hill, then that means like.
Is it
If
most
it's like-
likely going down it when it was going up? Because
No,
your-
it's going.
You going?
because your time was shorter.
Which way would be easier to ride, uphill or downhill?
Yeah.
So wouldn't it make sense that this is me going down the hill, and on the way home I'm going up the hill? Because it's taking me more time to do it? Now, do we know that for sure? No, we would need more info. Right? Maybe I was really excited to get to my friend's house, so I rode really fast, and then I just dilly-dallied on the way home because I didn't want to go home. Yes, Davian?
Didn't you say like, how would you know like which house is where?
Well, we know that this is my house because it's my distance from home. So here I'm at home because I'm 0 feet from home. So I know that. I'm not guaranteed anything, right? I only can take this for literally what I see. But that's some info we could maybe fill in based on some more information that I'm sharing. How do we feel about that? Okay, so here's our goal for today.